A quadratic inequality in two variables can be written in one of the following forms. Y is less than ax squared plus bx plus c. Y is less than or equal to ax squared plus bx plus c. Y is greater than ax squared plus bx plus c, or y is greater than or equal to ax squared plus bx plus c. In order to graph a quadratic inequality in two variables, there are 3 steps. The first step is to graph the parabola. Just like as if it were an equation. Keep in mind though, that if it's greater than or equal to or less than or equal to, use a solid curve. Because the boundary points would count in that case. If it's just greater than or less than, use a dashed curve to signify that the boundary doesn't count. Step 2 is to test a point. Since it's not equal to, I'm using the dashed curve. So there's my parabola, now I have to use a test point. I'm going to use the test point 0, 0, so this is just outside of the parabola. So I'm going to plug it into my original inequality. And I get 0 is less than 1, which is true. So I'm going to shade toward my test point since it makes it true. So that means that my shading goes here. And that's my completed graph for the inequality y is less than x squared plus 2x plus 1. Graphing a system of inequalities is the same process. So this top one is in standard form, but it also doubles as vertex form because I can think of it as x minus 0 squared minus 3. So I know my vertex there is at 0, negative 3. So I'm going to go ahead and plot the point 0, negative 3. And now I need some additional points. So I'm going to plug in 1. I'll get 1, negative 2. And I'll mirror that on the other side of the vertex. And I'll plug in 2. I'll get 1. I'll mirror that on the other side of the vertex. And I'll do one more point. Because with systems, it's really important to have a very accurate graph so you can see where they intersect. So 3, we're all the way up at 6. Again, dashed curve, because we can't be equal to. Okay, so now the bottom one is definitely standard form. So from my vertex, I'm saying B over 2A. Plug it in to find the y value. And we get y equals 4. So the vertex for that one is at 1, 4. Now I know this parabola should face down because the a value is negative. So they're going to be intersecting definitely. The y-intercept is at 2, so I can plot that point and mirror it on the other side of the vertex. And I'll go ahead and plug in 3. This time I get to use a solid curve because of the equal to. So there's my second parabola. I'm going to use 0, 0 as my test point since it's not on either parabola. So when I plug 0, 0 into the top one, I get 0 is greater than negative 3. Which is true, so I'm going to go toward my test point, so I'm going to stay inside the brown parabola. I'll plug 0, 0 into my second inequality. So 0 is less than or equal to negative 2 times 0 squared plus 4 times 0 plus 2. So I get 0 is less than or equal to 2, which is also true. So for the red one, I'm also going to head toward my test point 0, 0, which means this little overlap region here is the true shaded region, the solution to that set of quadratic inequalities. A quadratic inequality in one variable can be written in one of the following forms. Ax squared plus bx plus c is less than 0. Ax squared plus bx plus c is less than or equal to 0. Ax squared plus bx plus c is greater than 0. And ax squared plus bx plus c is greater than or equal to 0. We can solve quadratic inequalities using tables, graphs, or algebraic methods. So let's take a look at the first example by using a table. So with x squared plus x is greater than or equal to 6, we're actually going to put it in standard form. X squared plus x minus 6 is greater than or equal to 0. So we're looking for all of the x values that make that inequality larger than 0. So we have a table of values here. I'm just going to plug in x values and test and see when that's true. Where are the x-intercepts and when are we above the x-axis. So if we plug in negative 6, we have 36 minus 6 minus 6, which equals 24. So that's definitely above 0. Then we plug in negative 5. We get 25 minus 5 minus 6, which is 14. So again, we're still greater than 0. Plug in negative 4. We'll get 6. So I'm getting closer to 0, but still above it. Plug in negative 3. So 9 minus 3 minus 6. And we get 0. So there's our first x-intercept. And we keep going. Get 4 minus 2 minus 6. We get negative 4. So there's our first value that doesn't work. We're now less than 0. Plug in negative 1. We get 1 minus 1 minus 6, which is negative 6. So still below 0. Plug in 0. Get 0 plus 0 minus 6. So again, we're still below 0, and we start to see that your vertex would be at negative 1/2. Plug in 1. Get 1 plus 1 minus 6, which would be negative 4. So we're starting to climb back up. Plug in 2. We get 0. So there's our other x-intercept. And we already start to see the symmetry in the table. And 14. Okay, so we wanted all the values that make it greater than or equal to 0. So here we're greater than or equal to 0, and here we're greater than or equal to 0. So the solution to this quadratic inequality is x is less than or equal to 3, or x is greater than or equal to 2. The other two ways you can solve a quadratic inequality in one variable are by graphing, or you can do it algebraically. So let's take a look at graphing first. Number 4 is again in vertex form. Standard form. So we have to start by finding the vertex. So x equals the opposite of b over 2a. So it's negative 3 over 1, which is negative 3. So then y equals 1/2 minus 9 minus 2. Would be negative 13/2, negative 6.5. So we'll plot our vertex at negative 3, negative 6.5. Our y-intercept is negative 2, so we can plot that and mirror it. And then maybe I'll plug in one more point if I plug in 1. We get 3/2 or 1.5. Alright, because it's just less than, we use a dashed curve. And then, again, they wanted to know when it would be less than 0. So less than 0 means below the x-axis. So between here and here, it's less than 0. And so we would need to say that it's between the x-intercepts that the parabola is less than 0. So we're going to have to find the x-intercepts, so we can do quadratic formula for that. So x will equal the opposite of b, plus or minus the square root of b squared, minus 4 times a times c all over 2a. So negative 3 plus or minus the square root of 9. Half of 4 is 2, so negative 2 times negative 2 will be positive 4 over 1. So we get negative 3 plus or minus the square root of 13. So negative 3 minus the square root of 13 be the lower boundary. So when x is greater than that, but less than negative 3 plus the square root of 13, the parabola is less than 0, right in between its two x-intercepts, here and here. Okay, so we can also solve it algebraically. So if I get this into standard form, I can factor it, and I'm going to solve it just like it were the equation x squared minus 3x minus 4 so that I can find my x-intercepts. So I'm going to get my x-intercepts to be 4 and negative 1. So I'm going to plot those points on my number line. And so now I just have to figure out which area satisfies the inequality. So if it'll be in the middle or on the outer ends of the number line. So I can use a test point like 0 in my original inequality. And you have to do the test point in order to know how to do your signs. So I'd get 0 minus 0 is less than 4, or 0 is less than 4, which is true, so I know this section makes the inequality true. So I'm going to say negative 1 is less than x, which is less than 4. That's the region that satisfies the given quadratic inequality. So if we give you a quadratic inequality in one variable, you get to decide, do you want to solve it with a table? Do you want to graph it? Or do you want to solve it algebraically and use a number line to test and see which direction your signs should go? All three will work all the time. You get to pick which one is your favorite. Unless, of course, we ask you for a specific solution method on an assessment.